Hey guys, welcome back. All right, another week in the books, another week ahead of us. Okay, so this week we're going to talk about your boy Charles, right? Charles Law, that is. Okay, so last week we had Boyle's Law, and Boyle's Law said that volume and pressure were inversely proportional, which meant as one went up, the other went down. Think about squeezing a water bottle, right? I increased my pressure, my volume went down. It got smaller. I pushed those molecules closer together. Okay. Charles' law is going to talk about volume, but this time instead of comparing it with pressure, we're going to talk about temperature. And this is one of those things, again, you guys know this and you understand this, all right? But oftentimes when we do this as like a science class topic, you make it more complicated than it needs to be. Think about this. Think about if you have a basketball, right? And you leave it outside, okay, over the winter. When you pick up that basketball, right? Suppose it was a summer, it was inflated, it felt really firm, and then you go outside in the winter and you find it under a tree. I don't know why you're looking under a tree in the winter, but you are, and you find it. Is it going to be as full or is it going to be flat? Maybe not a basketball, a soccer ball, whatever. Okay, it's not going to be as intense. It's not going to be as full. It's going to feel like it's flat. If you go to bounce that basketball, it's not going to bounce back up the way it should. And the reason for that is because your temperature has decreased. And because your temperature decreased, your volume decreased. So Charles' law states that temperature and volume are directly proportional. That means that as one goes up, the other goes up, right? If my temperature goes down, the volume of that basketball is going to go down. If the temperature goes up, the volume of that basketball is going to go up, all right? As one goes up, the other goes up. One goes down, the other goes down. And the fact is directly, it means that it's like the same. So if I were to double the temperature, I double the volume. If I were to cut the volume in half, or I were to cut the temperature in half, the volume would get cut in half. Okay? So what I do to one happens to the other in the same proportion, that same amount. All right. And why is that? All right. And I think the easiest way to think about this is to think about a balloon. That's my balloon. And that, if you can see down there, is my campfire. I've got my logs and I've got my fire. All right. Somebody learned how to draw in the quarantine. So these little dots in here are my molecules. So what happens to a molecule or a gas molecule, a gas atom, as I add heat to it? Going back like 4 lessons. Remember I had that chart up here and it said as you add heat, you add kinetic energy, they move faster, right? You have a solid, it has a vibrational, and then you go movement, and then you go to a liquid and it's like that sliding, and then you have a gas and it's like okay? So we add heat, we're going to add energy to those molecules, which means it's going to bounce against the walls of this balloon a lot harder, thus increasing the volume, okay? Now, if I were to remove that fire, okay, those molecules are going to slow down and my balloon's going to get smaller. In one of the videos that you'll watch, a guy dumps, I think it's carbon dioxide or liquid nitrogen onto a balloon. And that balloon goes like this, and it shrinks. The temperature goes down. Those molecules, they come closer together because they move slower. They're not all over the place. The amount of space they take up decreases. Their volume decreases, so they come closer together. And then as that liquid nitrogen kind of wears off, you'll see the balloon gets bigger and bigger and bigger. Those molecules start to spread out more, okay? It's really simple. We add heat, molecules move faster, they take up more space. We cool things down, molecules come closer together, they take up less space. The amount of space something takes up is its volume. Think about, last example I'll give you here, I'm going to keep this as like a little shorty instructional video, is think about if you have a pool float, okay, and it's laying like next to the pool, and it's 100 degrees outside, and that pool float feels like it's going to pop, and you put it in the water, and you go and you lay on it, and you have yourself a nice lemonade while you're laying on that pool float. And then after a couple minutes, it feels like it's lost air. And you're like, yo, this thing has a leak. It actually doesn't have a leak. The pool water is colder than the air temperature. So those molecules inside your pool float, they come in contact with that water, and then they start to slow down, so they come closer together. Thus your pool float feels like it has deflated, when in actuality it hasn't. You've just moved those molecules closer together. They're taking up less space. Therefore your pool float doesn't feel as inflated as it would normally. Okay? That is Charles' law. Temperature and volume are directly proportional, which means as one goes up, the other goes up. That's it. Done, done, done.